for 3 and it will find you the parent to be.
Hello. 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 Okay then, so we're gonna start with the graph series of striver. At the moment I'm at this joint set, so we'll be proceeding with this only today. Graph series of striver. At the moment I'm at this joint set, so
Ultimate.
I hope it's
3
audible.
1 1 4 for himself. So again a path compression will happen. Yes. When you find the parent, 3 will give you as 4. So the path compression will also happen. Find parent of 3 will give you 4.
Yep.
3 1 1 4 for himself. So
All working, so let's do a 2 hour stream for this. So um, the initial start is gonna be like I'll just start the video again.
hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So, in this video, we're going to learn about the most important topic in the graph series, which is the disjoint set data structure. It's a
So let's start with whatever I know about this topic as much as I have covered. So initially what's happening is that basically we are being given these uh, I would say pairs that we have to join, and we are being given these pairs that we have to join, and then we will be required to have a rank. So the disjoint set basically means like if 3 and 4 are the disjoint, yes, because they don't have anything common. So we will be having a rank and a parent. So initially what's gonna happen is that we will be increasing that rank and the parent one by one step at a time. So like for example, uh, if we are having at the moment with us 1 comma 2, and yeah, and then we have 2 comma 3, 4 comma 5, 6 comma 7, 5 comma 6, 3 comma 7. So if that's something that we are having, what we could be doing is that we could be having a thing known as the rank and then a thing known as parent. So we're gonna keep updating those rank and the parent array each time we form a reversal. Initially the concept is that, for example, let's start from the start.
there's two options. One is finding the parent. That's one of its main functionality, and the other main functionality is union. Now, this union can be done with two methods. One is rank, other one is size. I'll be discussing both of them. But so primarily, it gives you two functions: find parent and union. Now, I did talk about dynamic graphs, graph changing configurations. So let's understand this. Now, what do you mean by these things? These are all edges. There's an edge between 5 and 6. Okay. So initially, what we assume is 1, 2, 3, 4, 5, 6, 7. Union in disjoint set will do it for you. We'll talk about union in details, but as of now, know the higher level of union. Union will go and connect. So what I'll do is I'll go and connect. Okay. Done. Next, 2 and 3. Connect 2 and 3. Next, 4 and 5. Connect 4 and 5. Next, 6 and 7. Connect 6 and 7. So you see the graph is changing at every instant. But you'll be like, but Striver, wait, this is how graph is formed. But what happens here is if I stop the formation right now and I give you a question where after this formation, I suddenly ask you, hey, does 4 and 1 belong to the same component or not? You will say no. Why? Because 4 as of now is here, 1 as of now is here. Till this point, they're not in the same component. So the answer will be no. So in any stage, someone might come up and ask you, because the graph is changing at every step, but I can ask you a question at any step, and you should be able to answer that in constant time. That is what disjoint set will do, and I'll explain you how it does. Next, 5 and 6. Let's connect.
Alright, so basic principle of disjoint set is being that it's gonna be telling us, is this connected or not in constant time. That's it. I mean, do they belong from the same set or not?
So the answer will be no. So in any stage, someone might come up and ask you, because the graph is changing at every step, but I can ask you a question at any step, and you should be able to answer that in constant time. That is what disjoint set will do, and I'll explain you how it does. Okay. Till this point, they're not in the same component. So the answer will be no. So in any stage, someone might come up and ask you, because the graph is changing at every step, but I can ask you a question at any step, and you should be able to answer that in constant time. That is what disjoint set will do, and I'll explain you how it does. Next, 5 and 6. Let's connect 5 and 6. Next, 3 and 7. Let's connect 3 and 7. Now if I ask you the same question, does 1 and 4 belong to, like after performing all the operation, does 1 and 4 belong to the same component? Your answer to that will be yes, they do belong to the same component. Understood? So you saw, till here the graph was something different. The moment you performed the next two operations, the graph was a combined one. So I can ask you this particular question, or any U and V belong to the same component at any particular time. But this is the use case of disjoint set data structure. Now let's quickly check out what is find parent and what is union exactly. So in order to implement disjoint set data structure, we can implement union in two ways. One is the rank, the other one is the size. So I can follow two ways of doing it. Okay, but initially I'll be teaching you the rank. I'll be coding you up, showing you how to write a clean code so that it can be reused in almost all the problems. And then I'll be teaching you the size one. So the video will be first union by rank, then union by size. Okay, so let's understand rank. So in order to implement union by rank, we'll be requiring a couple of arrays. One is the rank array, while the other one is the parent array, which will serve for finding parent. I'll explain you. So let's quickly assign the rank and the parent arrays. Okay, so the initial configuration is very simple. What we do is we assign a rank array with the
Alright, so this was like union by rank.
same size of the number of nodes. Since the graph is 1 based indexing, I start the array from 1. So everyone is assigned to 0. Okay, so what does rank 0 mean? So if you see this particular node, there is no one beneath it. So it means there is no one beneath it, 0 nodes beneath it. But eventually, with the optimizations that we will do, the meaning will change. So I'll explain you throughout the course. So now we have a parent array. Now remember, initially everyone is the parent of himself. Now what does parent mean? Parent, okay, right above guy. That is what is the definition of the parent, which is stored here. Again, over the course of this lecture, the definition of parent will change as we do multiple optimizations in order to obtain a constant time complexity. So this is what we currently have. Let's quickly start the operations. So let's quickly write the pseudocode for the union of u comma v. So remember, the step one is very simple. The step one says find ultimate parent. Yes, find ultimate parent of u and v. What is the meaning of ultimate parent? I'll explain you. And we can term this as ultimate parent, like ultimate parent of u and v. Let's term this as pu and pv. Pu means ultimate parent of u. Pv means ultimate parent of pv. Now find rank of those ultimate parents. Find rank of pu, pv. Find rank of ultimate parents, not u and v. Ultimate parents. Okay. Now connect smaller rank to larger rank. Connect smaller rank to larger rank always. In case of equality, you can connect anyone to anyone. We will explain that as we move. Okay, cool. We have understood or have written the pseudocode. Okay, let's now quickly check out the first operation that has been asked for us. It says union of 1, 2. So what I do is I have 1. So I go and look at the parent of 1. What is the ultimate parent? You have a bunch of nodes. The guy at the top is known as the ultimate parent. Okay,
So initially we have to assign the ultimate. So initially the rank that has been assigned is 0 to every node out there, and the ultimate, like the parent array, so every node is parent of itself. So that's that. So starting from like the first node, looking at the connections that are being like formed here, what we can be doing is that we can be like, all right, now do we have to connect 1 and 2? Yes, because that's what we have to create, an edge between 1 and 2. So we have to make an edge between 1 and 2, and then the thing would be like so we'll be checking as in terms of the rank and in the terms of parent. So when we are going to check rank, we're going to find out the ranks of both 1 and 2 at the moment are 0, and as the ranks at the moment are 0, what we will be doing is that we will also be checking the ultimate parent, and then we will be figuring out that the ultimate parent of both the nodes are the nodes itself. So that means that we can join any node with each other, like we can join 1 and 2, or we can join 2 and 1. So doesn't matter who stays on the top if that's the situation. So ultimately the answer, the node system would become like if it comes to like joining the nodes, we would be like, all right, 1 with 2, fair. So the moment we have joined 1 and 2, what we would be having is that now the rank of 1 is gonna get updated because we joined 1 and 2. So the rank of 1 would be getting updated, and the moment rank of 1 gets updated, we will be seeing that the parent of 2 is also gonna get updated because we joined them like 1 above and 2 below. So 2 is going to have 1 as its parent. So if we have like the rank and parent thing, so here the rank 1 2 3 4 5 6 right? Initially it all was the node itself. Now for 1 the rank became 1, because obviously for 1 it became 1, because now 1 is like at a height of 1, so that's the rank. And then what do we have for 2? The parent of 2 is 1, because obviously, and then else all the nodes are going to have rank as 0 at the moment, and parent of every node is going to be the node itself except for 2. So yeah, that's how we fill the array. So now we move ahead. Now what we are given next is 2 comma 3. So now we need to form an edge between 2 and 3. How that's gonna happen is like we're gonna check the rank and the ultimate parent both the times. In every case, I would say. So we're gonna check the rank of 2. The rank of 2 in this case would be 0, and the rank of 3 also would be 0, but the parent of 2 would be 1, the ultimate parent of 2 would be 1, and the ultimate parent of 3 would be 3 itself, right? So now in this case, what we are gonna understand is that how do we combine these things?
For 1, who is parent of 3? 3 itself. What's the rank? Rank of this particular 1 is 1. Rank of this particular 3 is 3. If the 1 is 1, 3 is 0. Sorry, it will be 0. It's 1 over here. And is the 1 the top guy? It is. So the ultimate parent of 2 is 1. Who is the ultimate parent of 3? 3 itself. What's the rank? Rank of this particular 1 is 1. Rank of this particular 3 is 3. If the 1 is 1, 3 is 0. Sorry.
Alright, so the rank is always gonna be of the ultimate parent. So so for the understanding, if like the rank of 2 is the ultimate is it streaming? The ultimate rank of 2 is 1. No, the ultimate rank of 2 is 0. Sorry, there's nothing such as ultimate rank. It's parent or it's ultimate parent or rank. So the rank of 2 is 0, and the rank of uh, 2 is 0, and the ultimate parent of 2 is 1. Alright, so that's the catch. That's where I was wrong. First of all, consider the ultimate parent and then consider the rank of the ultimate parent. So ultimate parent of 2 is 1, and the rank of 1 is 0, and ultimate parent of 3 is 3 itself, and the rank is again 0.
It will be 0. Who is the greater guy? This one. The 3 will come on the top guy. It is.
Alright, so rank of 1 is 1. My bad. Rank of 1 is 1.
So the ultimate parent of 2 is 1. Who is the ultimate parent of 3? 3 itself. What's the rank? Rank of this particular 1 is 1. Rank of this particular 3 is 3. If the 1 is 1, 3 is 0. Sorry, it will be 0. Who is the greater guy? This one. The 3 will come up and get connected to the this one.
Alright, understood. So ultimate, so now ultimate parent of 2 was 1, ultimate parent of 3 was 3. So we're gonna see in terms of rank whose rank was greater, so that is gonna get connected, is gonna be on top. So the rank of 3 was less than the rank of 2, so 3 came below. Understood. Now next we have to connect 4 and 5. 4 and 5 would be connected in the same way 1 and 2 got connected, so no worries. Same goes for 6 and 7. So now we have 5 comma 6. 5 comma 6, we will be referring to the rank of 5, the rank of the ultimate parent of 5. First of all, always consider the ultimate parent of 5. So we're going to consider the ultimate parent of 5, that is, the ultimate parent of 5 is 4, the rank of 4 is 1. That's the thing. The rank of 4 is 1, and side by side we will be updating the rank and parent arrays as well. So this is done for 5. Now for 6, we're going to see that the ultimate parent for 6 is 6 and the rank of 6 is 1. So now in this case, when the ranks are same, in case of 5 also, in case of 6 also, the ranks are same. So what are we going to do is that we can do like connect either of those. Like we can connect if like the rank is same and everything. So what we can do is like, so 4 5 and 6 7, so the ranks are same at the moment. So what we can do is all the connections are going to happen from the starting node. All right, the root of the parent node, that is the point from where we are going to connect any always. So either we can connect like 6 and 7 with 4, or we can connect 4 and 5 with 6 and 7. So we can also do 6 7 and then connect 4 and 5. So it's gonna look like this a little bit, the bottom one. The thing is that all the connections are gonna happen anyhow from the root or the parent node. Wait, are these two things same? Here. Yeah, so in this case the root and the parent node were same. So yeah, that's that. So we can have like both the cases.
Small object 4, and I erase this thing, connect apparently of the same ranks. So either this can go and get attached here, or either this can go and attach it. You can do as you wish. So what I'll do is I'll just go ahead and take the 6 and make it attached to 4. Done. And now omit this. Remember one thing, you attached 6 to 4. So the parent of 6 will be 4. The parent of 6 will be 4. Remember this very, very well. Okay, next.
So attachment is going to happen and the parent has to be updated in the same manner. So the parent could be different. That's the thing. And the rank of 6 then would become
at rank 1. So since you attached same guys, height will, if you see the height increased, so apparently you go ahead and say the rank to increase by 1 more, so the rank will be 2.
Alright, so rank of 4 would be 2. So rank of 4 would be 2 then. Alright.
So this is where we stand till we have.
Next is 3 comma 7. So let's see how do we proceed with that. We have 4, we have 5, 6, and we have 7. Next is like 3 comma 7. So what's the ultimate parent of 3? That's 1. What's the rank of 1? That's 1. What's the ultimate parent of 7? That's 4. What's the rank of 4? That's 2. So rank of 4 is 2. So the whole section of, so then again 3 was not the parent, same goes for 7. 7 was also not the parent. Here we can see 3 is not the parent, 7 is not the parent. So we took the ultimate parents 4 and 1, you know, for 3 it's 1, for 7 it's 4, talked about the ranks of them both 1 and 4, and now what we are going to do is we are going to connect either this with this or this with this, depending upon who is having a greater rank. So here we saw that the rank of 4 is greater, so this whole thing would get connected to 4. That's the thing.
We have not performed the last step. Now, you've kind of understood everything. Now, suddenly if someone comes up and says, let me write it, does 1 and 7 or do 1 and 7 belong to same compo? If I ask you this question, the answer is no. But how will you find out? This is where something like find parent will help. This is where something like find parent will come into picture. Okay, so since I'm saying find parent will come into picture, let's understand. So when I'm saying does 1 and 7 belong to the same component, I look at the parent of 1, it's 1. I look at the parent of 7, it is 6. So I'll be like, okay, the parents are different, they're not. But wait, you should not do like this. Just imagine. You were having an 8 here. Imagine. Guys, I'll ask, does 8 and 7 belong to the same component? Now, something to notice, we're not creating a graph. We're creating a different data structure here. A graph is not being created. Okay? A different data structure is being created. If I ask you if 8 and 7 belong to the same component, ideally they should. But if you will look at the parent, then 8 would have stored 5, 7 would have stored 6. Both have different parents. Can you actually tell on the basis of parents? Or do you need the ultimate parent, the top guy, the boss? You need the boss, you need the
So like that's the thing, we would be needing the ultimate parent to tell like if they belong in the same component or not.
ultimate parent. So this is why. If I'm asking you who's the parent of 7, you say the parent of 7 is 4. So you go 7, you say 6. You see 6, you see 4. You see 4, you see 4. Oh, I'm the boss. That's why my parent is me. That's why you say the parent, ultimate parent. Boss is 4. And the boss for 1 is 1. So both have different ultimate parents. If both have different ultimate parents, you say they do not belong to the same component. This is the use of find parent. Now since you're creating a kind of a tree structure, the tree will increase in depth with more number of edge additions. The tree will increase. So it will end up taking log n. It is theoretically proven. The tree will increase and will end up taking logarithmic of n if you just apply union by rank. Because in order to find the parent of 7, you have to go from 7 to 6. From 6, you have to go to 4. And at 4, you find he is himself. You get the top boss or the ultimate parent. That's going to take you a logarithmic of time. But wait, that's why you said it works in constant. It does. We apply something as path compression. Okay, so what I do is, I say, okay, someone did ask me to find the parent of 7. So what did I do? I went to 6 because 6 was his right father or the next parent. And 6's parent was 4. And 4 says, I'm the parent. So you can write something like this. Okay, I went from 7 to 6, 6 to 4. So I know the 4 is the parent. So once you have figured out 7's parent is 4, and since we're just dealing with parents, and that is what I require, because our main goal is to figure out who is the ultimate parent. So can I say, once I've gone to 7 to 6 to 4, and once I figured out the parent of 7 is 4, can I actually say, I don't need this link anymore. I don't need this link anymore because I know 7's parent is now 4. So can I change 7's parent to 4? I can, because the next time, if someone again comes up and says me, hey, does 2 and 7 belong to the same component? And you again go and call find parent, you will not move like 7, 6, 4. Because this time, 7 will directly go to 4 and it will find him to be the boss. So you did a path compression.
So basically the need of path compression was that wait a second, find parent union rank size. So alright, so this was like of disjoint, that in this joint we would be having like find parent, and then we would be having union, out of which we would be having either by rank or by size. That's the thing. So what's the need of find parent? Find parent is taken in consideration to reduce finding of parent from reduce the finding of parent from log n to constant in a tree, because what we are having at the moment is a tree. So finding and traversing into the tree would be like log n. So we need to reduce that towards an n or a constant. So that's what find parent is for. Yeah, that is what find parent is for, and that's it, I guess. That's the use of find parent, and that's why we take it into consideration path compression, right? So that's where path compression comes in place. Used for reduction of log n to n. Yep.
Ultimate parent, the top guy, the boss. You need the boss, you need the ultimate parent. So this is why. If I'm asking you who's the parent of 7, you say the parent of 7 is 4. So you go 7, you say 6. You see 6, you see 4. You see 4, you see 4. Oh, I'm the boss. That's why my parent is me. That's why you say the parent, ultimate parent. Boss is 4. And boss for 1 is 1. So both have different ultimate parents. If both have different ultimate parents, you say they do not belong to the same component. This is the use of find parent. Now since you're creating a kind of a tree structure, the tree will increase in depth with more number of edge additions. The tree will increase. So it will end up taking log n. it is theoretically proven. The tree will increase and will end up taking logarithmic of n if you just apply union by rank. Because in order to find the parent of 7, you have to go from 7 to 6. From 6, you have to go to 4. And at 4, you find he's himself. You get the top boss or the ultimate parent. That's going to take you a logarithmic of time. But wait, that's why you said it works in constant. It does. We apply something as path compression. Okay, so what I do is, I say, okay, someone did ask me to find the parent of 7. So what did I do? I went to 6 because 6 was his right father or the next parent, and 6's parent was 4. And 4 says, I'm the parent. So you can write something like this. Okay, I went from 7 to 6, 6 to 4. So I know the 4 is the parent. So once you have figured out 7's parent is 4, and since we're just dealing with parents, and that is what I require, because our main goal is to figure out who is the ultimate parent. So can I say, once I've gone to 7 to 6 to 4, and once I figured out the parent of 7 is 4, can I actually say, I don't need this link anymore. Or I don't need this link anymore because I know 7's parent is now 4. So can I change 7's parent to 4? I can, because the next time, if someone again comes up and says me, hey, does 2 and 7 belong to the same component, and you again go and call find parent, you will not move like 7, 6, 4. Because this time, 7 will directly go to 4 and it will find him to be the boss. So you did a path compression. You said, once I will just compress you. And then I know that, hey, listen, your parent is this guy. I know this. I don't need to go via 6. Imagine the tree to be longer. Imagine the tree was something like this. Just imagine. Take it as an imagination. Imagine the tree was something like this. And someone said, find parent of 5. So what will you ideally do? You'll go to 5, you'll go to 4, you'll go to 3, you'll go to 2, you'll go to 1. And at 1, you'll find he's the parent himself. And you'll say, 1 is the parent. You'll say, 1 is the parent. But what I will do is, I'll do a path compression. I know 1 is the parent. And 1 will be the parent of 2 also. So I'll say 2 is directly correct. 1 will be the ultimate parent of 3 as well. So I'll say, 1 will be the ultimate parent of 4 as well. So I'll just remove this and say, and I know 5's ultimate parent will be 1. So apparently, a tree which was something like this, if you do path compression on finding parent of 5, 4, 3, 2, 1, and you get 2 as a parent, it returns 1, it returns 1, it returns 1, it returns 1, it returns 1. Because you went, and you backtrack to get 1, 1, 1. So what I'll do is, when this guy will return 1, I'll say 3, your ultimate parent is 1. Why are you connected to 2? Why are you wasting your time getting connected to 2? 3 will be like, yes, does make sense. Let me connect to 1. 4 will be like, yes, I'm also wasting time. 5 will be like, I'm wasting time. Everyone goes and gets connected. So this is how the graph will change. Now, under 1, we will have 2, we will have 3, we will have 4, we will have 5 directly. Yes. So we know this is for sure. And next time when someone comes up and says, find parent of 4, I'll be like, array, 1, direct, low, 1. Because 4 is connected to 1 and we parent everyone in the path whom I encounter. I'll replace their links and attach it to the direct parent. But here comes a slight twist. I'll attach it to the direct parent, so it's fine. So what we usually do is, we attach it to the direct parent, and that's what we call as path compression, okay? Remember this. So as of now, we have something like this. Now what will happen is, the next 3 and 7 will come. So I'll be like, you have to attach 3 and 7. So we know 3's ultimate parent is 1. And that's very easily found because 3 is directly attached to 1. But when I try to find out the 7, I'll have to find the parent of 7, which goes to 6, which goes to 4. And in order to find the parent, we will end up doing a path compression. So let's be honest, let's do the path compression, which will be something like this. And I'll find the ultimate parent of 7 to be 4, who is connected to himself, right? But if you do this, the tree will be something like this. And the rank of 4, if you carefully observe, is 2. But actually you have 5, 6, and 7. Ideally the rank will also decrease, but we cannot do it. We cannot do it because we're not sure of it. Because the rank cannot be reduced in while path compression. The simple reason is, imagine you had something like this. And someone asked you to find a parent of 8. So you went ahead and found parent of 8 and path compressed. So you reduced one section of the tree, but the other section is still having a bigger length. So the rank cannot be reduced. So that's why we call it as a rank and not height. If we can reduce it, we would have called it as a height. But since it cannot be reduced, we call it as a rank. Rank in the sense means this guy is bigger than this guy. Sorry, opposite. This guy is bigger than this guy. That's it. That's the meaning of rank. This guy is higher ranked than me. Got it? So the moment you find the parent of 7 to be 4, I find the rank to be 2, which means this is the bigger guy. So the smaller guy will this time come up and get attached to this guy. So what will happen is, this guy will come up and get attached to this one. So ultimately what we will have is, the parent of 7 will be 4, and I'll attach 1 to 4. So what will happen? The parent of 1 will now become 4, correct? So if I just draw it, it's going to look something like this. 1 attached here, and 2 and 3 attached to this guy, correct? So will the rank change? No, it's still the larger guy. Attaching a smaller to the larger guy will not impact, because the rank of 1, if you remember, was 1, the rank of 4 was 2. So we are not storing the height, because during path compression, the height will shrink. So this is how easily we can do it. Now if after this someone comes...
So like, even if we have like attached rank and everything, the thing is that even if we have compressed the path or something, and the rank becomes like 1, because it's going to be stagnant or something, the rank won't be changing. It's going to remain whatever we had it input as.
Someone says, hey, does 3 and 6 belong to the same component? What do you do? You'll call the find parent for 3, and you'll find the parent to be ultimate. 3, 1, 1, 4 for himself. So again, a path compression will happen. Yes, when you find the parent, 3 will give you as 4, so the path compression will also happen. Find parent of 3 will give you 4, find parent of 6 will be directly 4. So both of them have same parent or ultimate parent, so they belong to the same component. Quite easy. Since you're compressing the tree, the tree will be always of very limited size. In order to find parent, you have to do limited traversals, always. Got it? So thereby the time complexity in order to perform the union operation is big O of 4 alpha. Now this 4 alpha has a huge mathematical derivation, which is not required in interviews. You can say 4 alpha, which is as good as constant, because alpha's value is very, very close to 1. It is as good as a constant. And in order to find parent, it is also 4 alpha. So overall the data structure works in big O of 4 alpha. Remember this, okay? So the question comes up, but Trevor, how do we do path compression? You might be thinking, how do you do path compression? Because it looks scary, because if you're connected to this, then you're connected to this, then you're connected to this, then you're connected to this, how do you path compress? Nice. So 5's parent is 4, 4's parent is 3, 3's parent is 2, 2's parent is 1, and 1's parent is 1. So what you can do is you can backtrack. So you can write something as find parent and you can give the node u. Okay. And what will happen is you will say if u is equal to parent of u, then return this u. So basically, what does this mean? If at any moment 1 comes, 1 will be equal to parent of 1 because parent of 1 is himself. So return the parent as 1. That's the basics. Because that is where you stop. Otherwise, you will be like, can you please return find parent of u? What does this mean? Imagine I give you 5. What will happen? It will go and say parent of 5. What's parent of 5? 4. It will go and say find parent of 4. So the next time find parent of 4 will happen. Does not obey. Again, it will say find parent of 4. What's parent of 4? 3. So it will go on. So the recursion will be something like this. Function of 5 calls function of 4, calls function of 3, calls function of 2, calls function of 1. At 1, the base case is executed. And when it is executed, it returns 1. So this 2, which you would have called 5 equal to parent of 1, it looks scale because if you're connected to this, then you're connected to this, then you're connected to this, then you're connected to this, how do you path them? It's very simple. So 5's parent is 4, 4's parent is 3, 3's parent is 2, 2's parent is 1, and 1's parent is 1. So what you can do is you can backtrack. So you can write something as find parent and you can give the node u. Okay. And what will happen is you will say if u is equal to parent of u, then return this u. So basically, what does this mean? If at any moment 1 comes, 1 will be equal to parent of 1 because parent of 1 is himself. So return the parent as 1. That's the basics because that is where you stop. Otherwise, you will be like, can you please return find parent of u? What does this mean? Imagine I give you 5. What will happen? It will go and say parent of 5. What's parent of 5? 4. It will go and say find parent of 4. So the next time find parent of 4 will happen. Does not obey. Again, it will say find parent of 4. What's parent of 4? 3. So it will go on. So the recursion will be something like this. Function of 5 calls function of 4, calls function of 3, calls function of 2, calls function of 1. At 1, the base case is executed. And when it is executed, it returns 1. So this 2, which you would have called here, what you'll do is you'll say parent of u will be 2. So when it will return with 1, you'll say, hey, 1, keep it. Right? Keep it 1. Next, you'll again return 1. You'll again return 1. So now 3 will also keep 1. Parent of 3 is 1. Next, you'll also return 1. So now parent of 4 will also be 1. Next, you'll also return 1. So parent of 5 is equal to 1. So everyone in turn will assign 1 to it. If everyone assigns 1 to it, so automatically all the links will be path compressed and pointing to 1 and all these links will be destroyed. Perfect. Done. So I hope you understood everything about union by rank and the path compression. Now it's time to code it up. So I'll try to create the data structure in a class so that going forward in the upcoming problems, we can use that snippet of code to solve almost all the problems. So we have a class of this joint set. Nothing to worry, like don't get too worried about a class. Very simple. It's a very simple thing. What's the initial configuration? Initial configuration required a rank and a parent. So just have it. And declare.
Alright, now what we can do is we can try to code it ourselves, right? We can just, take the understanding from ChatGPT and try to code it ourselves. Yep, so I have to code. This one set using what method did we use? Union by rank. We need to do union, so I want you to help me build the code by giving me what? Steps in brief to do it, so I can understand what is being asked in each step and what I am required to do. Oops. Thanks. So later you must maintain core requirement parent array. All right. Initialize every node as its own parent. Okay. And Alright, so we can have a parent array, we can have rank array for the height, or for the rank to be precise. And then we can also have step by step operations, initialize. Alright, n independent elements. What you do for every I for 0th I, parent and rank interpretation. Each element is is its own set, and every tree has height 0. Alright, so wait, disjoint set union by rank GFG practice. Yep. So we are talking about the union one. So are we like provided with the parent array? N K queries. Let's see.
Everything afterwards public. So all the functions can be reused outside. So now go ahead and declare the constructor. What's the construction? What is the constructor rather? So if you remember, I said you initially rank will be marked with zeros, parent will be marked with themselves. That is what we do. So we say rank dot resize of n plus 1 comma 0. Why n plus 1? Imagine it's a 1 based indexing graph. We need the nth index as well. If it's 0 based, fine, but declaring it as 1 n plus 1 will work for both 1 based as well as 0 based. Similarly, we can define parent dot resize of n plus 1 and we can keep it. And then we can go ahead from 0. Very, very important to go till n for 1 based indexing. And it'll be I itself. So this is how the constructor will look like. Now what
And the I, we have like in this joint set class, we have two lists, and then we have a function that's joint set, and then we have find parent function. And what this function is doing is simple, I guess. It's just talking about find. So initially here we are initializing it, right? uh, here we have initialized it, the disjoint set function, and we are saying like for int I, just do one thing, add 0, and in parent keep adding the I. So parent of every element would be itself, that's I. And then the next thing that we are having is like find u, like find ultimate parent, wherein we are like uh, so initially it's like find u parent, find the ultimate parent if node equals parent dot get node, return node, and if that's not the case, then ultimate parent is like find ultimate parent dot get node parent dot set node ultimate parent, return that. Alright, so we can ask it to get explained. Let's see.
What does disjoint set give you? It gave you find ultimate parent, right? So this will be the node, and for this you have to find the ultimate parent. So you know one thing, if node is equal to the parent of node, this is the ultimate parent for sure. So you go ahead and return the node. But if it is not, then you call the ultimate parent and say go to its parent and then look for parent, 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 parent. But this is the normal logarithmic type. We need the path compression. So this is where I can say whenever it returns the value, I'll store it so that in future if someone comes up and does ask me the same question, I can tell him that this is the parent. So this is where the path compression. Now what does disjoint set give you? It gave you find ultimate parent, right? So this will be the node, and for this you have to find the ultimate parent. So you know one thing, if node is equal to the parent of node, this is the ultimate parent for sure. So you go ahead and return the node. But if it is not, then you call the ultimate parent and say go to its parent and then look for parent, 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 parent. But this is the normal logarithmic type. We need the path compression. So this is where I can say whenever it returns the value, I'll store it so that in future if someone comes up and does ask me the same question, I can tell him that this is the parent. So this is where the path compression comes in. Path compression done. Next, what I'll do is I'm like, okay, void union by rank is what I need to implement. Union by
So what this function is doing is that it's like if node is equals to parent node, then it's of itself, so we're just returning node. And if that's not the case, then we're gonna put that thing again. So suppose it was 5. Yeah, suppose it was 5, then uh, is it like that? No. Then what we would have done is that we would have said that, yeah, alright, so if suppose the node was 5, here we would have said if node is equals to parent node, where here it would have been 4. So then this would have been false. We would have came down, return parent node equals, we were gonna store it, and we would have said find u again parent node. Now parent, in parent array we would have put 5, and here it would have been 4. So 4 equals parent of 4, that would have been 4. So yeah, then return 4, and we would have returned 4. Here it would have been 4, so parent of 5 would have been 4. Understood?
By rank. So I'll have node u and node v, which I have to combine. So ultimate parent of, I guess ultimate parent of u will be find ultimate parent of u. Similarly, you can say ultimate parent of v will be find ultimate parent of v. Now I can say if ultimate of u is equal to ultimate of v, I can simply return. What does this mean? If they're belonging to the same component, I don't need, right? But if they're not belonging to the same component, I go ahead. The first thing I do is I check if the guy parent of v. Now I can say if ultimate of u is equal to ultimate of v, I can simply return. What does this mean? If they're belonging to the same component, I don't need, right? But if they're not belonging to the same component, I go ahead. The first thing I do is I check if the guy u is smaller than the guy v, right? So if v is the greater guy, the smaller goes and gets attached to the greater guy. So the smaller will now say, okay, I'll go and have the parent as v. No change in rank, because if the smaller guy gets attached to the larger one, there'll be no increase, or that still stays the larger, right? Next, else if rank of ultimate of v, if this is the lesser guy, the rank of ultimate of u, if this is the lesser guy, then I say the opposite. I say parent of rank, parent of ultimate of v goes and gets attached to u. Perfect, done. But what if they are same? If they're same, I'll say attach v to u, you can the other way as well. U to v is okay as well. well, and rank of ultimate of u will increase because that is where I am attaching it to. We attach to u, so the larger one will grow in size. So this is what I'll do. Once I've done this, I can say the union is done. This is how our data structure will look like. How can we use this snippet of code? So I'll just hard code it to show you how can we use it. It's pretty simple. So you can be like disjoint set ds. What is the number of nodes? So in our case, it was 1. So I can have it as disjoint set of 7. So it will call this constructor ultimate of v. If this is the lesser guy, rank of ultimate of u. If this is the lesser guy, then I say the opposite. I say parent of parent of ultimate of v goes and gets attached to u. Okay, done. But what if they ask, does ask me the same question, I can tell him that this is the parent. So this is where the path compression comes in. Path compression done. Next, what I'll do is I'm like, okay, void union by rank is what I need to implement. Union by rank. So I'll have node u and node v, which I have to combine. So ultimate parent of ultimate parent of u will be find ultimate parent of u. Similarly, you can say ultimate parent of v will be find ultimate parent of v. Now I can say if ultimate of u is equal to ultimate of v, I can simply return. What does this mean? If they're belonging to the same component, I don't need, right? But if they're not belonging to the same component, I go ahead. The first thing I do is I check if the guy u is smaller than the guy v. Right. So if v is the greater guy, the smaller goes and gets attached to the greater guy. So the smaller will now say, okay, I'll go and have the parent as v. No change in rank because if a smaller guy gets attached to the larger one, there'll be no increase, or that still stays the larger, right? Next, else if rank of ultimate of v. If this is the lesser guy, the rank of ultimate of u. If this is the lesser guy, then I say the opposite. I say parent of parent of ultimate of v goes and gets attached to u. Perfect, done. But what if they are same? If they're same, I'll attach v to u. You can do the other way as well. U to v is okay as well. And rank of ultimate of u will increase because that is where I am attaching it to. V attached to u, so the larger one will grow in size. So this is what I'll do. Once I've done this, I can say the union is done. This is how our data structure will look like. How can we use this snippet of code? So I'll just hard code it to show you how can we use it. It's pretty simple. So you can be like disjoint set ds. What is the number of nodes? So in our case, it was 1. So I can have it as this. Right. Next, else if rank of ultimate of v. If this is the lesser guy, rank of ultimate of u. If this is the lesser guy, then I say the opposite. I say parent of parent of ultimate of v goes and gets attached to u. Okay, done. But what if they are same? If they're same, I'll attach v to u. You can do the other way as well. U to v is okay as well. And rank of ultimate of u will increase because that is where I am attaching it to. V attached to u, so the larger one will grow in size.
Alright, so pretty simple execution of find parent and then union by rank. Yeah, I guess. What's the stream status? Union by rank. Yeah, I guess. What's the stream status? Alright, so let's code this. So initially what he had was like rank and parent, I would say. I mean, how is the Java code looking like? In this joint set you have two things. Alright, so yeah, let's have a list integer, right, which could be parent, new array list. We could be having another one as rank, and that's it. For find, what we could be doing is base case, because this is going to be recursive. If why can't we have arrays for it? That is the question. Why can't we have arrays for it? Just a second. So coming back to the question, int find int parent and int x. All right. So if um, it's gonna be like we are given the parent array, but what's that about? Wait. Give Java solution of this. Union xy, refine x. I'm confused because it's like what has to be considered, like array list or the array or something. Public class main static int parent static int rank static void make set int n. Alright, so they have used arrays, but wait a second. Nope, 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 nope. And that is the issue. This is something. Oh, wait a second. What's this? What is this? Ooh. So they have like initialized it. Yup. But how would I know if they have been like parent of what is what? If like parent of x is -1 understood return x. X is root, return parent of x equal find parent. Find parent x. So inside the parent array, so where is the initialization of parent array? Like here they have given something else, here they have something else. Wait. Am I allowed to solve it? Union by rank. Yeah, so they have given it like differently, right? They're like having create your thing right here, and then you have U and V, U and V, U and V. I guess this makes more sense, but alright, let's deal with this first. Um, correct Java solution for this template. So initially for everyone we discussed that the node itself is the parent. Here it's -1. Cool. And the moment we find it, suppose we found out and let return x, we returned it. Are we updating parent anywhere else? Here it's that. Here it's happening. Like in union set, we are like find parent of that, find parent of that. In union, what we are doing is we are like find parent of x in the parent array, find parent of z in the parent array. If the parents are not equal, like what if like it's -1, then it's if parent of root x is not equal to that, So initially, this is the doubt. -1, so no parent exists initially. Critical realization sounds as though being a root is not permanent. Inside union set here too. So initially, if it's like if like you are finding, so if like find if parent of x equals -1, then return x. If it's not -1, then return if it's like, then we can return simply the int find parent int x. If parent is x, then we can be like return x, and if we return x, suppose parent wasn't that, so we can suppose if like parent of suppose 5 was in -1, that means it's not the root node, then we're trying to find the ultimate parent. So what's parent? So we can be like parent of x, like whatever it was, find, we can pass parent, and then we can pass whatever that value was, like 5, it's like 4, so we can pass like parent of x, right? And then what happens here is we join them. So here we are like, so int root x is find parent and find for x, same for z. And then if like the root x is not equal to root z, then we can be like root x is not equal to root z, then it's like your parents aren't the same. So yeah, we can combine them. Here it's not talking about rank or something, it's like union find. I mean, Alright, so we are just saying if it's not equal, then parent of root z equals root x. ChatGPT keeps telling me like it was like zero based indexing, but here it's from 1 to 10. So I'll have to see the solution. Yep. Return parent. It's like parent find parent of. Wait, what? So like it's confusing. Like, how is this thing causing issue? I mean, I'm saying that like the parent of z becomes x. Simple. That's on me. How do I attach it? I'm saying that parent of root node z is now x, so I'm putting x on the top and z below it. Yeah. So the merge structure is yeah. Alright, so base case is explicit in correct recursion solves only when this line moves, the recursion must have been to EGFC comp. Let's do one thing, let's just change it to this and to this and then run it. Still giving me a stack overflow. So the actual reason for stack overflow, your find assumes x is root, uses I is root. Wait, no, so root of individual elements are they themselves as the index? Now you land on the correct mental model, the CFG, let's log it in cleanly. Root representation in this problem, part I, if it's x, return x. So, this was easy, but ChatGPT fooled me in my understanding. I don't know why. Union by rank, we didn't do it. Disjoint set union by rank, union by size. GFT union by rank. Where can I practice it? So it's available like here only. Yeah. if we have to solve it, then this is like for union by size. This is for union by rank. This is for the code of find. This is for disjoint set int n. So design is a disjoint set, also called union find, data structure that supports the following operations. Disjoint set int n initializes the disjoint set with n elements. Void union by rank. N elements. So here we can have like int rank as new int of n. Same goes for this, where we can have parent. We can be like arrays dot fill rank with 0, and for int I equals 0, I less than n, I plus plus okay, so they have a solution. All right, for int I, it's like it's 0. I can be like parents I should be I. Yeah, simple. Is dot fill rank 0 for int I less than n, I plus plus parent I. Is dot fill rank 0 parent I guess it's done. Yeah. In find, what we will be doing is that we can have like if why am I having two things in find? See, I should be having one, right? I'm having two right here in find as well. Just a second. Alright, so we'll try to finish this quick. Yeah. Union by rank. And then, yeah, we'll end the stream. Can't understand why do they have int u and v in terms of the find. I mean, I'll have to just find a single thing, right? Wait. Int parent, int size, int rank, class disjoint. Alright, in class I have to do this. In public disjoint, in resize the arrays. Alright, +1 +1 +1. Okay. I don't care about size abhi. I have rank and parent. So I'm like, initialize each node with its own value. Cool. Understood. And parent. Public int. Would you have a boolean? Wait. Okay. Oh, okay. If two nodes are in the same component or not. And then u v public nodes, u and v if it's like in the same, so that is what it is for. Like if u is equals to that, find u ultimate parent of u if it's like if it's equals to v true, then they both are in the same. Alright, so this is for like actually telling. And u and v union by rank. Here we are going to perform the union, the if else thing. Understood. Union by size, uv. This is not of the concern at the moment because we haven't studied it till now. It's gonna come ahead, I guess. So yeah, let's start by solving it. Yup. Working well or not? Working well or not? Gonna come ahead, I guess. So yeah, let's start by solving it. Yup. Public disjoint said this is fine, I guess. Aristotle rank with. Should I be filling like the ranks with 0 or -1? What is this question gonna ask? Alright, so I guess I don't have to do this because initially in an array that's non-initialized, it's gonna be 0 by default, I guess, so that's no worry. here it's less than equal to. Here I have also done this for rank parent. So I do this control X parent. Here rank equals +1 parent of the whole for loop parent xi. Yeah, I guess it's fine. Yeah, now we can focus on the solution. That is public int find int node wherein I'm like, okay, public int find int node, and I'm like, if node equals parent node return node, so I'm going to return that only. And if it's not equal to that, then I'm going to return parent of that node equals find node, that is parent node. So if it's like node is equals to the parent node, that is if node is equals to itself, I'll just return it. And if node and the parent of that node are the same, that is if 5 is equals to 5, then return 5, right? If they're not the same, then just find out, like parent node is 5, so parent is gonna be what? That's gonna be find parent node. I'll put in whatever the value was. If node was 5, whatever the value of the parent node, that was 4, was. So if it's like 4, it's if like 4, I'll return 4, and I'm going to be like, here it's gonna be 4 here, so the parent of 5 is gonna be 4. Understood? Yep. So I guess the find is done, and then here I can have like return So here if it's like the ultimate parent is the same, then I am just returning it. Mm. If it's like ultimate parent of u and ultimate parent of v, it's like find ultimate parent, find ultimate parent. If I found the ultimate parents, and then it's like if it's like different, yeah. If it's like the same, I just return because they belong to the same component. Otherwise, join the nodes to the other node having the higher ranks among the two. But the thing is, if suppose they're having different parent, for example, but where was the rank ever? Rank is same 0 0, rank is same 0 0. All right. So if the rank is same, okay, understood. If the rank is same, if both have the same rank, join any node to the any node and take the rank. Yeah, makes sense. So the thing is, like, if here you're gonna say int ultimate parent u is find u v if up u is less than, no, if it's like equal to up v, you see. So then we don't need this, we can just return. And if rank of up u is less than rank of up v, we can say like, why didn't I start this? If rank of up u is less than rank of up v, then we can say parent of up u is up v. Yeah. Else if opposite of this happens, v is less and up u is more, then up v, control C, up v is like u. Yeah. Else if the ranks are same, then parent of wait, here it's not about it, here it's about this. We parent of u would be else I would just say that do one thing, parent of u becomes v, and that's it. And rank of v plus plus, right? Yeah, I guess makes sense. I guess it makes sense. I guess. Yep. Yep. UV. Find up. Up. If ultimate parents equal, return. If rank of ultimate parent u is less than rank of ultimate parent v, parent of u is v, blah blah blah. Else parent of u is, yeah, they have done that, so I did that. Understood, makes sense. Now that's union by size. Union by size is basically like get the ultimate parents of both the nodes, return the nodes already belong to the same component. Otherwise, join the node belonging to the smaller component to the node belonging to the bigger component. Parent of size is less than the parent, the size updates. Else size updates. Oh, alright, so in size it's more like in rank it's about oh, okay, understood.
So this is what I'll do. Once I've done this, I can say the union is done. This is how our data structure will look like. How can we use this snippet of code? So I'll just hard code it to show you how can we use it. It's pretty simple. So you can be like disjoints at ds. What is the number of nodes? So in our case, it was 1. So I can have it as quick same. So this is how you can always use the data structure. If you want to have two disjoint set data structure, you can go as ds1. You can have two different objects of this class, and you can have two different graphs and two different data structures. So this code can always be reused in almost all the problems because it covers up 0-based indexing graphs as well as 1-based indexing graphs. Now, question might be coming to your head, but Trevor, we did not understand why connect smaller to larger. Like, what's the idea of connecting smaller to larger? The first idea is I don't want to increase the height. For example, if I have 1, 2, I have a 3, 4, 5. Just for an example, empty. So if I connect the larger to the smaller, see what will happen. 1, 2, 3, 4, 5, 6. So basically, the height increases. And if the height increases, like we will do path compression for sure, but if the height increases, what happens is, in order to find the parent of 6, we'll have to travel 6, 5, 4, 3, and then 1. So you're taking a longer distance. So imagine someone would have said for 4. So you're actually taking a longer distance. And if you do the opposite way, which is saying, let's connect, like you keep 3, 4, 5, 6, and let's connect 1 and 2. So if you see for 6, the distance taken is shorter. Even for 5, the distance taken is shorter. Even for 4, the distance taken is shorter. But for these, the distance will increase. Like for 2, the distance will be now more because over here 2 was just traveling once and getting the ultimate. But over here, it has to travel to 1, then to 3. But the number of nodes over here are lesser. So the travel time for all the nodes computed will be lesser. Over here, the number of nodes are larger. The travel time for all the nodes will be larger. So to give you a clear vision, imagine we had something else. Imagine, okay, 5, 6, 7, 8. Okay, and we had 1, 2. Now, if you attach this guy to this guy, what will happen is, in order to find the parent of 7, 7 will go to 6 to 4, 3 to 1. Similarly for 8, 6, 4, 3, 1. Similarly for 5, 4, 3, 1. Right? So this will take longer time. This will take longer time. This will take longer time. More nodes will take longer time. Whereas if you attach this to this, they will take the similar time that they were taking, and only 2 nodes will take slightly longer time, which is okay. This is the reason we attach smaller to larger. First, to keep it shrinked. Second is to make sure that the time taken in finding out the parents is as minimal as possible. So you must be thinking, Striver, if that's the case, why are we using something like union by rank? Because after path compression, it doesn't even give us the height because the height is distorted after path compression. Can we use something as size which keeps a track of what is the size of the component? I think we can. I think we can. So that's what we will be doing. Okay. So what I will try to teach you now is union by size. We know find parent, we know path compression, but instead of rank, we'll be using the union by size. So over here, the same thing will happen. What is the size of the component? I think we can. I think we can. Is as minimal as possible. So you must be thinking, Striver, if that's the case, why are we using something like union by rank? Because after path compression, it doesn't even give us the height because the height is distorted after path compression. Can we use something as size which keeps a track of what is the size of the component? I think we can. I think we can. So that's what we will be doing. Okay. So what I will try to teach you now is union by size. We know find parent, we know path compression, but instead of rank, we'll be using the union by size. So over here, the same thing will happen. We will have a size array of the same size. So let's quickly declare the size array of 7 size. So the initial configuration will be very straightforward. We'll have a size and everyone will be of size 1. Why? Because everyone is itself a component when we start off with. So everyone is going to be having a size of 1. And we know one more thing, that the parent will be themselves. So this is what we take. Now to start off with, very simple. We say 1, 2. We say 1 has a size of 1, 2 also has a size of 1. So both are similar size. So it doesn't matter whom you attach. So I go ahead and attach 2 over here. The moment you attach 2 to 1, the size of 1 will increase to 2 because it took a size of 1, got attached to it. So the size increased by it. Okay. Next is 2 to 3. Very important point to realize. Now 1 has a size of 2. And remember the parent of 2 is this type 1. So 1 has a size of 2 and 3 has a size of 1. So this is the smaller. Goes and gets attached to 1. So goes and gets attached to 1. So the size will again increase by 1. Why? Because 3 was the size of 1. Perfect. Done. And 3 will be having a parent of 1. So this is also. Next is 4 and 5. So what I'll do is I'll just comment this. And I'll just assign 5 to this guy. And 5's parent will be 4, and 4 will increase the size of 2. Next will be 6 and 7. So I'll assign over here. I'll assign 7's parent to 6, and I'll increase the size over here. Perfect. Done. Next is where you understand. So next is, so 6, 7 is done. Next is 5, 6. So where is 5? 5 is here with 4. And 6 is here. So both of them, if you see, are of size 2, size 2. Same size. So what you'll do is, probably you can take 6 and get attached to this. Done. 6's parent will be 4. 6's parent will be 4. And since you're attaching a size 2 to 4, the size will increase by 2, not by 1. So basically, this is keeping a track of how big is this. This is keeping a track of how big is this. This is also done. Next will be 3, 7. So for 3, it's 1, which is the size of 3 size component. For 7, if you see 7 has this, which is nothing but a 4 size component. This is a smaller one, so this is keeping a track of 2. Same size. So what you'll do is, attaching a size 2 to 4, the size will increase by 2, not by 1. So basically, this is keeping a track of how big is this. This is keeping a track of how big is this. This is also done. Next will be 3, 7. So for 3, it's 1, which is the size of 3 size component. For 7, if you see 7 has this, which is nothing but a 4 size component. This is a smaller one, so this will go ahead and attach. So when you try to find the ultimate parent of 7, definitely path compression will happen. Here's the first step. Next, for 3, the parent is 1, so this goes and attach. 4's size will be increased by 3. The 4 will be having a size of 7. So you can keep a track of size. And this actually is much more like intuitive, you can say, instead of the rank. I don't find the rank to be that much intuitive, but I find this union by size to be much more intuitive than union by rank because it kind of makes sense when you're storing the size because rank is distorted. So what I'll do is, I'll try to copy the same thing. And I'll create in the same function, I'll just create union by size.
Alright, so what we have to do is just add the size that was before, and that's it, I guess. Yeah. So here, what we can be doing is that we can have a same thing with size. Yeah. Yeah. I guess we'll have to initialize size with also something, because there he took like size to be 1, but here he hasn't done that. Anyways, let's put that logic into use. We can be like int size of u equals what? I mean, I'll have to find.
Because everything else will stay same, union by size. And now what I'll do is, I will say, okay, fine. I know one thing for sure. Now I'm doing a comparison on the size. So size of this, if lesser than size of this, then I'll be like, okay, I will take the ULPU attached to the ultimate parent of V. Done. Next, the size of the ultimate parent of V, because it is getting attached to, will be increased by Q now is everyone will be of size 1. Why? Because everyone is itself a component when we start off with. So everyone is going to be having a size of 1. And we know one more thing, that the parent will be themselves. So this is what we take. Now, to start off with, very simple. We say 1, 2. We say 1 has a size of 1, 2 also has a size of 1. So both are similar size. So it doesn't matter whom you attach. So I go ahead and attach 2 over here. The moment you attach 2 to 1, the size of 1 will increase to 2 because it took a size.
You know that find thing? I mean, it works in the parent array, right? The whole find scheme, like find. It's like if node is equals to, so like we return node and everything. So I guess it works into the parent thing, but I mean, here we can be like, yeah.
Not by. Keep a track of a comparison on the size. So size of this, if lesser than size of.
Alright, we're just talking about the ultimate parent only. And then we are like, if size, if size of u is greater than size of UPV, UPU is greater than size of that. So what we are gonna do is we're gonna be like parent of UPV is UPU and size of UPU plus equals size of UPV. Else if that is not the case, if that's not the case, then size of u was greater, so parent of v was greater, so parent of u would be v and u and v, yeah. And if like else if like the size was same, if like sizes were same, then we could be like, let's do one thing, let's keep this as it is, and we can be like we can have like this only. Yep. Yeah. guess this would make more sense for the size thing. Union by size of UPU. Okay, this condition we can have like right here. Where like if size is like this, parent size plus else. Why don't we have a condition if size are the same?
This, then so the ultimate pattern in equal keys. If there is an equal keys, it will be increased by ultimate pattern of view. Else, now will there be an equal keys? If there is an equal keys, you still attach it, right? So we can just write an else instead of writing else if greater than else, because an equal doesn't matter whom you attach to, right? So I'll just take this and I'll just change this to v, I'll change this to u, I'll change this to u, and I'll change this to v. That's it. So this is how the union by size will go. And what I'll do is, now remember, if you're implementing a data structure, either use by rank or either use by size. Don't use both of them together. Don't use both of them together because we have to declare a size this.
Okay, makes sense. So what do I do then? We'll do it afterwards, but I guess this is it. This code would work. Yeah. Yep. So I guess union by size and rank is done. I'll end the stream for the moment. Yeah. Until next time.